This is Lab 4 Circuits by Thomas Reid. For an introduction, the purpose of this lab is to predict the behavior of circuits containing resistors in series and parallel, and then use multimeters to measure the actual values of conventional current and potential differences in the circuits. And then we will examine the behavior of ohmic resistors and capacitors. For the initial findings, the current was found to be 0.02A in the 2-resistor circuit. The calculated and experimental values matched each other, and the time constant, which is RC, was 5.984 seconds. The key concepts of this lab are the node rule, which is the sum of currents flowing into a node is equal to the sum of currents flowing out of that node, and then the loop rule, which is the round-trip potential difference for static electric fields is 0 because of path independence, and the equations are pictured on the right. Additionally, electrical resistance, which is a physical property that depends on the material, and it is a measure of the opposition to the flow of the current. And the potential difference across a resistor of length L is shown by the equation below. Capacitance is a property of an electric conductor that can be measured by the amount of separated electric charge that can be stored on it per unit change in electrical potential, and the equation is also below. For the systems and surroundings, the system was an ammeter or voltmeter, the device measuring the current flowing through, and the surroundings was the circuit itself, as you can see on the pictures on this slide. Part 1, it was a simple series circuit with 2 batteries, 2 resistors, and 2 ammeters. The predicted current was 0.02 using the loop rule, and the experimental current matched that at 0.02, and the reversed ammeter value was just the opposite of negative 0.02. Part 2 was the open series circuit, which was the exact same as Part 1, except for the second ammeter is replaced by a voltmeter. The predicted values were a potential difference of 3 volts and a current of 0, and these predicted values matched the experimental values. Part 3 was a potential differences around the circuit, which is the same as Part 2, but closed the open circuit with a wire. Only 3 transitions between points in the circuit displayed a non-zero potential difference, which were A to B, C to D, and E to F, but this supported the loop rule as the potential differences added to 0 volts. Part 4 was an ammeter placed in parallel to a resistor. Same circuit, but the ammeter is now in parallel with the 100 ohm resistor. The current flowing through the circuit has increased to 0.06. The current split at the parallel resistor, making some current encounter more resistance while others did not. For calculating resistance, using Ohm's law, previously mentioned in key concepts, the resistance of each part of the circuit can be calculated. The 47 ohm resistor had 48 ohms of resistance, the 100 ohm resistor had 102 ohms of resistance, and both the ammeter and wire had 0 ohms of resistance. Part 6 was the RC circuit. This contained a 10 ohm resistor, 200 mF capacitor, and a 9 volt battery. And you had to switch from a 10 ohm resistor to a 20 ohm resistor, and you can see the differences in the charging and discharging times of these two experiments. So the greater the resistance, the greater the time it takes for that potential difference to reach the 0 current. Part 7 was a time-dependent voltage. This was an RC battery with 9 volt battery, RC circuit with 9 volt battery, 30 ohm resistor, and 2000 mF capacitor. For this part, for every second that passed, we must record the potential difference across the capacitor as it discharges. You then needed to plot the potential difference over time versus the natural log of the initial potential difference. We then solved for -1 over RC, and the RC being the time constant, which was -1 divided by -0.1671. Some possible sources of error: lack of precision in the calibration of the ammeter, unnecessary rounding during calculation, and timing errors when calculating potential difference times. For discussion questions, so what if we did this with an actual ammeter instead of an ideal simulated ammeter? How would it have affected the circuits that we hooked it up to? Since a real ammeter has non-zero resistance always, the current in the circuit would have decreased slightly, which would have decreased readings on the ammeter. Lastly, what if we used a real battery to charge a real capacitor with no resistor in the circuit? How would this have changed our model to predict the capacitor to reach full charge? The prediction of the capacitor reaching full charge almost right away would not happen in real life. The wires would have a non-zero resistance that would increase the time for the capacitor to reach full charge.